Welcome to Reimagine Mobility podcast series. I'm here with Brad Sheets. Brad's been with AVL for over 20 years. Welcome, Brad. Thanks for joining me.
Thank you.
Simulation. We've talked quite a bit already with some colleagues of yours regarding the different products and services AVL has, but I don't necessarily want to talk about AVL. We want to talk about simulation in general. And I think your experience, if it serves me well, my memory here, is really in the mechanical simulation space. So maybe give some of our listeners and viewers an idea. Well, what different simulation areas are there when you say you're more mechanical? So what are the other guys, and what does mechanical mean?
Yeah, so for mechanical, it started out being static finite element analysis, so just doing stress analysis. But as we get into engines, say, so 25 years ago, started working with engines, it got in more into the multi-body dynamics. So the interaction of each finite element model that you were making separately are now connected together inside of multi-body dynamics tools, for example, like Excite, which AVL sells and supports. And there, we're able to take do the full simulations and look at how the pressures from the combustion act on the piston, the loads travel down through the connecting rod, produce torque on the crankshaft, look at how the bearings are supporting these loads. And that's looking at, say, durability. So looking at the loads, looking at how things are going to wear or fatigue. And as a side product of those simulations, we also look at NVH, which is noise, vibration, and harshness. And that's really what you can feel, maybe for an automotive vehicle setting in the vehicle, and maybe at the beginning. I know my son's car, when it starts in the morning, it's trying to warm the engine up, so it's going through some things that are going to make the engine vibrate. That gets into the chassis, and that gets into your seat and onto your steering wheel. So looking at how things are vibrating, so those are more tactical. And then you have the ones that you can hear. So you have the frequency range up to, say, 3,000 hertz, where these parts are vibrating. Then that's moving the air that then gets to your eardrum, or it could be vibrating other parts. So that's multi-body dynamics, durability, NVH is where it's gone, really. So I think I answered your question there.
That's good. That's very good. So a lot of times when people talk in the simulation space, they talk about 1D simulation, they talk about 3D simulation, maybe other types of simulation. Can you highlight a little bit the difference between what those two, or maybe, again, additional ones really mean? And does it apply only to, let's say, electric vehicles? Does it also apply to things, as you just mentioned, basic engines, or engines that have been around for 25, 50 plus years?
Right. So on the structure side, predominantly people are talking about three-dimensional. So we're physically modeling the parts with finite elements, discretizing them up in 3 dimensions, where things are moving in the X, Y, and Z direction, but also have rotations. There is a subset of that where we look at early on in designing engines, or not just engines, but also motors and drive lines, which is torsional vibrations, where you can simplify the parts down to just 1 degree of freedom, which is predominantly just the rotation. So it's a spring damper system. So we simulate the cross section of a part, and then we can get the torsional stiffness of that. The forcing function would either be the electric motor poles as they pulse and causing torques, or it could be the individual firing of a cylinder causing those pulses down the system. So those cause durability issues. Those also call it NVH issues. So you probably felt that in your own vehicle, where you get maybe some shudder or something of this nature, where you're surging back and forth. So generally speaking, we're talking 3 dimensions, but there are subsets of doing 1-dimensional simulations.
Okay. And in the mechanical simulation, I know there's systems that we have that other ones has as well, as it relates to simulation. We also simulate not just maybe an e-motor, but the complete, let's say, electric propulsion system. Maybe not just a a combustion chamber, but the complete
Hmm.
engine. Is that something that is growing? Is this something that is depending
Yeah.
on if you're a systems guy versus a specific component or part guy more important? How is that?
I think on the electric motor side, there is the controls that we're trying to take into consideration as far as how the direct voltage has to be converted into an alternating current. The cleanliness, or how clean that current is if it's not done well, you have to convert something into digital, and basically you're making a sine wave ideally, but you can't do that because it's digital, so you're getting stair steps,
Mm-hmm.
and these stair steps can then produce torques that aren't perfect, and those can get into the system. So that is done on the control side, but we also have to consider how that could affect downstream on the durability side or on the torsional side.
I think systems we want to talk about, is are we
Yeah.
just looking at an internal combustion chamber, the simulation for it, or are we expanding to the simulation? I mean, to the system, right?
I mean, I could say that when we're considering systems on an engine, the internal combustion is performing. So we have fluid dynamics people that are simulating that. That gives us a pressure trace that can come into as our forcing function into our multi-body dynamics.
Okay.
The valve train is part of the gas exchange, so we are simulating valve trains in simultaneously with the crank train.
Mm-hmm.
And also, if there's any gear trains or pulleys or things of this nature, those are solved simultaneously. It's not always necessary to go all out and do all of those calculations. You can model them separately and decouple them, but in certain situations, it is important that there can be some coupling of those systems that can lead to things that you wouldn't see if you decoupled them.
Okay. Very good. So you're talking a lot about engines. It's still very much a field that
Yeah,
simulation is very important, maybe even more so, right? Less people are being
yeah,
deployed towards that because the human capital is deployed towards
yeah.
more evolving EVs and fuel cell based propulsion systems.
Yes.
So, in the space that we've talked about, and let's stay with engines again, gasoline
Okay.
or diesel engines, I've always wondered what's more important. Is the processing speed of a simulation tool more important for your customers, or is it more the accuracy, the correlation to the real world of the models that we're using, or does it depend on what somebody's trying to do?
I I think we're to the point where we can do both, actually. I was
Okay.
thinking about this in preparation that 25 years ago when I started doing this, we would model things on a pretty coarse approach. We were limited by our computing resources. I almost started back when you had to build finite elements by hand, nothing automated.
Yeah.
But we had to keep them small because you had limited resources with your computers. With Moore's law tracking along through the 80s and 90s, things were getting faster every year, every month almost.
Hmm.
That allowed us to not just look at what we normally would look at with, say, peak cylinder pressure or maximum torque or an overspeed condition where we're only looking at individual points throughout the whole load curve. But we are now able to look at the whole speed range from part load to full load. So we were able to do more. And the idea there is that there could be conditions that you would miss where torsional excitations could reach a resonance, could cause damage. And if you didn't do the so-called speed sweep of multiple loads and so forth, you could miss that. So computers allowed us to do that, to be able to submit multiple cases even of the same model. We have the luxury at AVL to have unlimited licenses, but you still can submit a lot of simulations.
Hmm.
And more recently, the post-processing is becoming automated.
Hmm.
So you would spend a lot of time just gathering the results and showing them. Now we have apps and so forth that create these for you automatically, and you're looking at things in a consistent manner, and even comparing models. The accuracy part, we've reached that accuracy. We have correlated models. We know the techniques that we need to do to get the correct stresses in a crankshaft fillet, say, and we have reached that accuracy. So we're able to do both, I believe, at this point. Yeah, accurate and quick.
Good. So maybe staying a little bit with this, I think it ties in nicely to my next question. If you were to pick over your last 25 years, your favorite simulation tool or simulation product, what would it be? And tell us a little bit, how has that tool evolved? And maybe you're picking a tool that we've had or that you've been using or supporting for 10 plus years, whatever it might be. But pick a tool that really is, again, hopefully one of your favorites, and tell us a little bit, how has this tool evolved? Maybe from exactly what we just talked about, processing power, post-processing power, modeling accuracy, the finite element analysis that maybe go into, to maybe even to the UX, the user friendliness, all of that stuff.
Yeah. So there's probably a couple of them, but I think I'll focus on what I've kind of almost become an expert in, I would say.
There you go.
And that's inside of Excite. We have the capabilities of not just solving the structures, but we also have the so-called elastic hydrodynamic joint, which solves the fluid film, or more particular, say the oil in the main bearing, or the oil film thickness in the connecting rod big end. And this was part of why I enjoyed multi-biodynamics when I started, and I saw this, and one of my first jobs was to work in this area. At the very beginning, it was groundbreaking, I would say, to be able to solve this, but it was very basic. It would solve the Reynolds equation for the fluid film simultaneously, but there was assumptions. It was fully filled. We couldn't model any oil grooves. We couldn't model any oil holes. And then over the years, those were added inside of Excite. So we could put the groove where the oil comes into the bearing. We could also model any deformations in the bearing due to manufacturing when you bolt up the main bearing cap to the block. And that was a big improvement to be able to get the boundary conditions right to get more accurate results. In the beginning, the joint was really to get the nice load distribution properly from the crankshaft to the block, but it evolved into being able to look at the details of the bearing. So we're talking very microns of closeness. And then that also involved into being able to not just solving the Reynolds equation, but we introduced the ability to look at friction from metal to metal contact, how the parts would, if the film thickness got small enough, how the peaks of the parts would touch each other and actually contact and cause additional friction. This can cause heat that has to be worried about. It can damage the bearing. And also we can simulate the wear. So we can progressively run a simulation, look at the load, say this is going to remove so much material based on models like Archer's Law. And then we can reprofile the bearing as if it were happening in real life and then run the simulation a second time. And I find this interesting that we can do this. And when you lay the part on the table and you do an Excite simulation, you can see very, very similar wear patterns.
Okay.
And I find that very interesting. And
that's cool.
Kind of pretty cool.
Yeah. So I think my next question has always been, I've always had this in my mind, this feeling of a simulation tool is super critical, obviously, on how accurate it is, right? So I get a closer correlation to real world data once I put the device, the engine in the case that we've talked today, together versus what I've had when I compare it to what I modeled, right?
Yeah.
But I always wondered how important to your customers, to our customers, or in just general to simulation tool and product users is the user interface and the user friendliness. So how easy is it for maybe a layman like me that a tool is easy to use and makes it real simple to get to running a model and get some data out of it? Or is this a different type of application? And some tools are very simple and they're specifically for, let's say, a layman like me.
Yeah.
And then there's tools that are really for the let's call it the nitty gritty engineers that want to go into the details. Let's call them the nerds, right? That really
Yeah,
want
yeah.
every little
Yeah.
finite data point. Can you share a little bit of a light on that?
Yeah, back in the old days, everything was command line driven. So you would type a command to make point A to go to point B,
Yeah.
and then as the computers came in and laptops became more popular and so forth, the graphics, and I'll admit, our tool is the Excite tool, for example, is I think probably 30 years old plus now. So the very beginning, we're still using some of those same graphics ideas, but we have recognized this as a company, and over the past several years, we've started to simultaneously develop, and now it's part of our offering is our simulation desktop, where that is more progressive. It is what I think new users would expect to see. The video gamers, if you will, where you have more flashy graphics. It's still the same solver in the background. You're still getting the same precise answers that you getting before, but you're getting more visual feedback as you assemble parts, as you put things together. In the past, I think you had to use a little bit more of your imagination because you didn't always have a 3D confirmation that you were putting things together correctly. So this, I think there's pros and cons in both. I'm kind of old school, and I think you should start from the bottom up and not jump in deep end head first. But it allows you, I think, now to maybe take those bigger leaps, and you have more confidence that you're putting things together. So I think as things progress, we have better tools to help us with these things.
Okay.
And a lot of these also have so-called apps in the background that are automating a lot of the steps that we've had to do manually.
Okay.
And this is important because you could get, say, the expertise of AVL. We'll put together a workflow, and a new user can follow this workflow. An experienced user could say, well, I like 99% of what AVL is doing. Maybe there's something I'd like to do here, so he can tweak that app. But I think this is an important thing that we're trying to help is to make more entry-level users become quicker experts.
Sure. And maybe last question, with all this, let's say, evolution of and progress we have from, again, simulation tools, and you mentioned 25 years ago to now, how this has moved, the UX, how that has changed. How do you stay up on the latest and greatest trends as it relates to simulation technology and maybe even simulation methods, right? I don't know how much AI is already playing a game or playing a big part in the simulation tools. ChatGPT now is this big, this big craze right now that we're trying to see where can we implement this almost anywhere. How do you stay up on trends? How do you stay up on what maybe makes sense, what doesn't make sense? How do you form your opinion? How do you form your professional know-how?
Yeah, I'm intrigued by what I hear about this AI. I think my only real exposure to this so far has been probably in the last 6 months or so, where part of what we were talking about earlier is when I was thinking about how things have progressed when we started just doing basic models. There was a point where we could start to do optimization or more DOEs because we could do more simulations. I think on the optimization side, we now have some tools at AVL that have some artificial intelligence built into them. So by running a few models, this thing learns how the behavior of the system is behaving based on what you've told it, and it more quickly guides you to the optimized direction. I find that interesting. It's probably a little bit above me. I try to read up on it when I can, but I learn about this, I guess, through osmosis by other people at AVL doing work and following their projects or following the reports that they put out. So.
Okay. Very good. Thanks, Brett, for your time, and thanks
You're
for
welcome.
our listeners and viewers tuning in. Thank you.
Take care. Bye.
Thanks for listening to Reimagine Mobility Podcast. If you like this episode, please subscribe and tell a friend.